I come from the Dr. Hugo and Dr. Balzer group from the University of Freiburg, with the report of anisotropy of PI-PI promotes low molecular friction. And we investigate this by AFM-based single molecule force spectroscopy. It is well known that lubrication is very important in industry across different length scales, from the very tiny working machines to the very big working machines. Then for all of these machines, the ideal properties would be a stable contact, but meanwhile a very low friction, and this would prevent the materials from damage. Now people have realized both the adhesion and the friction originates from the interfacial interactions. Therefore, to realize such ideal properties, the interfacial interactions has to be anisotropic, and they should provide a high adhesive force for maintain the stability and contact, but meanwhile a very low shear force for decreasing the friction. In our daily life, we can see such systems, for example, the magnet on our fridge. And if you want to pull the magnet out of your fridge, you need a higher energy. But if you want to pull it only laterally on your fridge, it costs much less energy. From the serious chemistry of aspect, we've rather try several different interactions, and PI-PI stacking would be an ideal candidate. And it is already well known that strength of PI-PI stacking is very sensitive to the geometry. And meanwhile, at the macroscopic level, PI-PI stacking involved interfaces like the graphene is observed with super lubricity, which means very low friction. Therefore, we believe PI-PI stacking is a very unique interactions which may help us to realize such ideal properties. So in our study, we would like to use single molecule force spectroscopy to study the PI-PI stacking at the single molecule level, namely a single pyrene molecule with 4 rings and with a HPG substrate. Here we, in the 2 different pooling modes, if we pull it vertically to separate the 2 molecules, we would measure the adhesion force of PI-PI stacking. And if we pull it laterally on the surface, we would be able to measure the friction force of PI-PI stacking. Then from both of the experiment, we can deduce the molecular mechanism of why PI-PI stacking could provide low friction. Our first experiment is to study the PI-PI stacking using vertical pulling, which means pull it perpendicularly to the surface. And to avoid the effects of the cantilever, the molecule is linked to the cantilever with a very long polymer chain. And if we pull it laterally, the chain is gradually extended until the molecule is detached from surface. As you can see here, you can see a small peak. Which is corresponding to the detachment force of the molecule from the surface. We did the experiment for different pulling velocities, and we find the force remains constant. That means the adhesive force of PI-PI stacking in this study is 36 piconewton. This force is not very strong, but still quite stable because it is even higher than some multiple hydrogen bonds. Another stage, we try to study the friction force of PI-PI stacking, which is divided into 3 steps. The first step is we elongate the chain for around 100 nanometer. This is to avoid the interactions between the tip and the surface, because tip is much bigger than the molecule, which have a strong effect if it is on the surface. And then we pull the pyrene laterally. If the pyrene is stuck on the surface because of the friction, we would be able to monitor the change of the deflection of our cantilever. After this lateral pulling, we further elongate the chain to detach the pyrene. This is to validate that our molecule is still on the surface. Okay, so this is one of the typical curve we obtained for the lateral for the friction force of pipette stacking. And you can see during this lateral pulling, which is stage 2, the vertical force is constant. This means no additional force is applied onto the cantilever. And when you move the cantilever, the pairing moves with your cantilever smoothly. So this means the lateral force is too low to be detected. And the friction force for pipette stacking is rather low. And after the lateral pulling, we again pull it vertically to detach the molecule. And we find the detached force is constant to the pure vertical pulling. This is proof that the molecule is still on the surface during the lateral pulling, and we are not marrying nothing. As a comparison, we studied the friction force of a thiol-gold coordination bond, which is a very strong chemical bond. And when we pull it, we find the friction force is very high, and both the adhesion force and friction force goes hand in hand and rupture at more than 500 piconewton. And from the force curves, we can see when the friction force is higher than 0.5 piconewton, it could be detected by our FM system. Therefore, for the pairing, because the lateral friction force is undetectably low, the upper limit force friction force should be 0.5 piconewton, which is 2 magnitudes lower than the vertical adhesive force of 36 piconewton. Then we estimate the friction coefficient just by routine Montan's law, which is the friction force equals to the friction coefficient multiplied by the adhesion force. Then we find for the thiol-gold coordination bond, the friction coefficient is higher than 0.8, which is a very high friction. But for the pipette stacking, the friction coefficient is equals or even lower than 0.01, which is a very low friction case and in the range of super lubricity. The comparison of these two interactions suggests pipette stacking is ideal for promoting low friction. We again did some more experiment to study whether the friction is.
You have 3 minutes left.
Thank you. Is still very low for on the whole plan. So we pull it forward and backward, or even with 2D sliding pattern. And in both the cases, we find the friction force remains undetectably low, which means the molecule can have no friction in any direction you pull it on the surface. The final thing we did is to study the stability of pipette stacking, because the interfacial interactions should not provide only low friction but stable contact. So the first experiment is we pull the molecule on the surface for 2 micrometer, which is much longer than the molecule size. And after the sliding, we find the molecule is still on the surface, as indicated by this detachment force. Another experiment is we apply a small force on the molecule and wait for 10 seconds. And after 10 seconds, we still see if we detach the molecule, it's still on the surface. So both of the experiment validate the contact is rather stable in the vertical direction. Finally, from the theoretical part, we study the molecular mechanism why pipette stacking is so anisotropic. So we analyze the free energy landscape, and we find the free energy barrier, free energy difference for the adhesion is around 100 kBt, but for the friction is almost 0. Therefore, when you pull the molecule vertically, you need much more energy to overcome this barrier, and therefore it represents as a much higher force. So that means the adhesive force is much higher than the friction force. For the potential applications, just a brainstorm that you can coat the working machines with pi molecules, which would provide you low friction and stable contact and prevents your materials from damage. So for conclusion, pipette stacking has a high adhesive force and a low friction force. And this anisotropy of pipette stacking makes it an ideal interfacial interaction for significant lubrication. And this is the first report of super lubricity at the single molecule level. Finally, I would like to thank Dr. Hugo and Dr. Balser for their support and guidance, and also all of my colleagues for their help. And I'm looking forward to talk to you in the discussion tab. Thank you.